Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening, I'm Yvonne, staff for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Tonight, we learn about the forces that produce earthquakes and tsunamis. Our distinguished guest is John Ebel, Professor and Chair, Department of Earth and Environmental Sciences at Boston College, and also Director of Boston College's Weston Observatory. Dr. Ebel received his Ph.D. in Geophysics from California Institute of Technology in 1981 and joined the faculty of the Boston College in the same year. Since that time, he's been in charge of the New England Seismic Network of Weston Observatory at Boston College, a network of seismic stations for the 6 New England states. Dr. Ebel's research focus is primarily earthquake patterns in New England and vicinity, although he's also published papers on earthquake activity in other parts of the United States and other nations. He's also conducted extensive research on methods for earthquake hazard computation and earthquake forecasting. He's been a consultant on seismic hazard and nuclear test ban treaty monitoring issues for the government agencies, including Argonne National Laboratory, the U.S. Nuclear Regulatory Commission, and Lawrence Livermore National Laboratory. He's been a consultant on seismic hazard for over 20 major engineering projects in the U.S. and other countries, and he served on National Research Council panels on studies concerning seismic hazard and low-level radioactive waste siting. He's received distinguished awards for his research and service. For additional information, please check tonight's event page on our website. And now we're very pleased to welcome Dr. John Ebel. Welcome, Dr. Ebel.
Thank you very much.
And I'll ask to start with, if you could please give us a little background on tectonic plates, these things that seem to be at the basis of everything. What are they?
The Earth is a solid body. But the interior of the Earth, the rock moves just a little bit.
I see.
It flows very, very slowly, except for the very, very outer shell. About 60 miles from the surface down into the Earth is quite rigid. And so the outermost part moves as a rigid or set of rigid blocks, and these blocks move, some move away from each other, as we have spreading at the middle of the Atlantic Ridge, Mid-Atlantic Ridge, and other spreading centers. There are places where one plate comes against another plate, slides back into the Earth, and then there are places where one plate slides laterally against another, as for instance happens at the San Andreas Fault in California.
I see. So it's not all the same kind of movement. It's all dynamic, but some of them are sort of overlapping and some of them are sliding against each other. Is that?
That's exactly right. There are different plate interactions in different places, and that gives slight differences in the way the earthquakes behave.
Evidently, it's a little different in the Pacific, for example, than in the Pacific Ring of Fire area, as opposed to the Atlantic Ridge. Is that the case, where we don't seem to have these huge things?
Iceland, for example, has spreading earthquakes,
That's true, yes.
Whereas Sumatra has subduction zone earthquakes.
Great point.
So very different in terms of the sizes, and somewhat different in terms of the effects also.
I see. Okay, when you have an earthquake, what's happening?
To a seismologist like myself, there are actually 2 different aspects to an earthquake. All right, an earthquake is caused because the rock is being squeezed much more strongly in one direction than another. It's kind of like putting a clay brick in a vise, and you crank the vise, increase the pressure, increase the pressure, increase the pressure. Rock is like brick. It won't withstand the pressure forever. At some point, the rock cracks, and it slides to release that pressure, to equalize the pressure.
Okay.
So when it cracks, that crack has a name. We call it a fault. And when it slides, The sliding creates vibrational waves, just as if you were to slide a heavy piece of furniture across the floor of a room. You feel vibrational waves. Those waves spread out, just as, for instance, if you were to have a clear lake on a very still morning, you toss a pebble in, you can see those waves go for hundreds and hundreds and hundreds of yards if you watch. Same thing happens in an earthquake. So if you're near an earthquake epicenter, the shaking is very strong. If you're a little bit farther away, the shaking is weaker. If you're farther away still, the shaking is weaker still.
Okay, that's good to know. Then a lot of earthquakes occur in the oceans, right? Or can they just be on land and everywhere?
They occur in the rock underneath the ocean floor.
Well, there, I understand,
And so as far as the earth is concerned, you know, it's rock cracking. And it doesn't care if there's water above or not. That's
or how
exactly
much.
right. We people seem to draw a difference, but the rock doesn't care.
Got it, okay. So then when you have the earthquake, then under what circumstances do you get something like a tsunami?
Earthquakes, as I said, cause the rock to crack. The rock slides on the fault and cracks. Now, if you have a water body above where the earthquake takes place, and the ocean floor is either shifted up or shifted down, if you think of a children's plastic swimming pool, put your hand underneath the swimming pool, suddenly push up on the bottom. The water has to readjust. So a wave moves away from where your hand was. Exactly the same thing happens when you have the faulting that moves the ocean floor up or down. That then causes the water to readjust, that sends a wave out, and that wave causes water to, for instance, push up onto the shore. And as it pushes up onto the shore, we have a name for that. We call it a tsunami. People think of a tsunami as a single wave, and they think of the Japanese print.
Exactly, the famous,
this big wave that comes in. But it's really like this flood that just keeps coming and coming and coming and coming. And it takes about 15 or 20 minutes for the tsunami phenomenon itself to come on shore. Some places it can be as much as 30 minutes. So then it comes on shore. Well, then the wave, once it's reached its maximum extent, then it drains away. But tsunamis oftentimes have multiple waves. So you can have one wave come, and then a half hour later another wave come, an hour and a half later another wave
that much time.
And you can have these oscillations for 4, 6, 8, 10, 12 hours, depending upon how the water's dispersed across the ocean basin. Usually the first wave or two is the worst, but once you've flooded an area, if you have buildings and they're getting hit by wave after wave after wave, maybe an earlier wave damages the building and a later wave then takes the building out.
Now, the tsunami has some peculiar features, right? So in terms of comparing it with waves, ordinary waves in the ocean, or rogue waves that are huge but spring up out of nowhere, are there some features about the tsunami that are quite different?
The
speed.
The wave itself, of course, it moves with a certain speed. But that speed depends upon the depth of the ocean water, where the wave is. So where the ocean is very deep, the water in the wave spreads out. So the wave only has a very small, what we call amplitude. It only has a very small height.
I see.
So when the Japan earthquake occurred, there was a big tsunami associated with that. Out in the open ocean, the tsunami was only about 6 to 9 inches high.
So you'd go right over it.
But it was spread over hundreds of miles.
Yes, I see.
And it was moving very fast. It was moving at several hundred miles per hour.
Yes.
As the water comes up on the shore, the water depth becomes shallower, the wave slows down. So instead of having a small amplitude spread over a wide area, what you have is now a slower moving wave where the wave is spread over a smaller area and it has a higher amplitude. So, this 6 inches in the open ocean now piles up to 30 feet by the time it gets to the shoreline, and that's what inundates.
Okay, so it's very fast. Is it true that it's as fast as a jet?
Well, and the open ocean, by the time you get to the point where it runs up on shore, it's 30 miles an hour.
I see. But
Maybe
with a
25
lot of
miles
force.
but with a lot of force. Water
Right.
has an awful lot of force.
Right.
And then,
Yeah,
of course,
okay.
people can only run at the fastest people at 20 miles per hour.
right.
The water's coming in at 25 to 30 miles per hour, and that's one of the reasons why you have so much loss of life when a tsunami occurs.
Exactly. Now, is the trick here is that it just keeps rolling because it's all backed up. This is huge. It's not a single wave, right? It's multiple. It's a group of waves.
Well, you have
or
one
force.
large wave that
Right.
comes in,
Okay.
and then as it goes out, the next wave is
I
coming
see.
in. Now, you know, the time between waves can be at half hour or
So,
an hour. And in fact, sometimes tsunamis, and this is a real problem in some areas, the tsunami actually starts with a withdrawal. It starts with a
Like to pull in.
out of the ocean. So you'll have the ocean pull out over 10 or 15 minutes. And that movement is fast enough that it can, for instance, strand fish on a beach.
Isn't that something?
And so you have some places where there have been deaths because the water withdraws.
Right.
People say, hey, there's
Let's
dead
go get
fish
dinner.
out there, let's
Yes.
go get dinner. They go running out, the water comes back in, it comes in faster than they can
Right.
run, and then they get inundated. So many primitive cultures, in for instance the Southwest Pacific,
Right.
they have stories among the people. If the ocean withdraws, you go
Run.
to the high ground. You run. That's exactly right.
Yeah, isn't that
That's exactly
something?
right.
That's quite amazing that you'd have that kind of a phenomenon, which is a little different from, I guess, normal kinds of waves. Is that the idea?
It's something that we normally don't associate with, you know, the way water waves behave.
Exactly. So now, normal waves are also surface, correct? They're not coming from the bottom of the ocean up. Is that correct?
The tsunami waves
Yeah.
are traveling horizontally. I mean, if you were
Yeah.
right above the earthquake,
Yeah.
there would actually be a component that would be going up.
Yeah.
But as soon as you get a few miles away from the earthquake
It's just
epicenter,
wave-like, but it's fast.
It's fast and it's traveling horizontally.
Yeah, okay. And then, before we leave that, can you distinguish that from a rogue wave? That these are terrifying to ships in the sea, apparently. Is there anything? There's no relationship between the earthquake and that, I'm sure. But
Right.
But rogue waves are very high. Tsunamis are not necessarily high when they get into the beach, right? Especially after the first.
That's right, yeah. If you're out in deeper water, you barely
Right.
notice a tsunami.
Right.
You know, the ships are safe. They don't have a problem. They only
Right.
have a problem if they're close to shore and the water pushes them up onto the shore.
Okay.
The rogue waves that happen in storms, for example, happen when the ocean is choppy and you happen to get just a proper constructive interference of different
Okay.
waves that give a very, very tall column of water. But
Just
you know,
out of the blue,
if you
yeah.
if you were in a ship and a rogue wave were to hit you, you would have been going up and down like this.
I see.
Whereas if you were in a ship, let's say a mile offshore of a tsunami, you barely notice the ocean going up and down at all.
So that's how people were very surprised in island nations like Japan and so on, that you could have people out fishing and so on, and they go back and their villages are missing.
That's
yes,
exactly right.
Okay. And then the earthquakes that cause tsunamis are in the ocean, right? Are there land earthquakes that can cause a tsunami?
If you have an earthquake on the land, almost all of the displacement is on the land itself.
Yeah.
So any movement in the water is so minor, it's never damaging. You know, with very sensitive instruments, we might sense a very slight water vibration, water
Okay.
change. But for all practical purposes, it doesn't mean anything.
Okay. How about these huge, or let's say, landslides or whatever, like we were talking about the Canary Islands situation? What about that? They say that you can cause a mega tsunami. Is that possible?
Well,
And what is that?
There were some calculations that some scientists had done that said if you had a major hillside collapse off a volcano, I mean, you have to be moving literally cubic miles of rock, and that were to happen all at once, they did a calculation that suggested that there could be a big wave that would move across the ocean and could be damaging far away. More recent calculations have actually disputed that.
Good to know that.
On the other hand, we do know that locally in bays, there have been landslides. For instance, in 1957, there was a large earthquake in Alaska. It caused a landslide in an enclosed bay. There were 2 ships that were anchored in the bay the night of the earthquake, and they got carried by the tsunami from this landslide, actually over the land, out into the ocean. One of the ships tipped over, was never seen again. The other ship made it, and the report of the people on the ship, they were holding onto the side of the ship. They were looking down in the water. They could see the tops of the trees.
Isn't that something?
In the water, under the boat, and they ended up being deposited out in the ocean. But that was just minor in that little inlet in the bay itself. By the time you got out in the ocean, of course, the most of the energy had been dissipated.
Yeah, but that's amazing, even within a bay. But that's probably quite rare.
Right, or a lake. I mean, these kinds of things are reported in lakes sometimes too.
Yeah, right. But that's just a huge, like, shelf falling off of a...
It was a major landslide off of a mountain.
Right. Well, so we understand now how tsunamis sort of operate, I guess. They're hugely damaging, and I guess the one in recent years in the Indian Ocean, right?
In 2004.
Just horrible thing. I forget, was 500,000 lives were lost and
hundreds
stuff.
of thousands, yes.
Right. They didn't seem to expect that at all. Why? Is that a region not associated with earthquakes, or they didn't have equipment or to detect them? Why would they not have any expectation that this was coming?
I think it's a stretch to say that there was no expectation.
Okay.
Because, in fact, 2 years before that earthquake, there had been a conference held about the possibility of tsunamis in the Indian Ocean. And scientists had gone along the shorelines of Sumatra and some of the other islands, and they had mapped tsunami deposits. They knew that there had been big tsunamis there. The problem was they had never had evidence of a major tsunami that had gone across the ocean basin to, for instance, India, or, for instance, to the African coast.
Yeah.
And people hadn't, because there was no record of that, scientists hadn't looked for tsunami deposits in those areas. And it's kind of the way we human beings do things.
Of course.
You know, if it's never happened, we don't think it can happen.
Yeah.
And, you know, a scientist like myself might come and say, well, it might be possible. And people will say, well, if we've never seen it, we're not going to go look for something we've never seen.
Right.
And so now we know that it can happen. Now there is a tsunami warning system for the Indian Ocean as well as for the Atlantic. Now there's actually one for the Pacific. There's warning for the Indian Ocean and the Pacific, but we also set up a warning system for the Atlantic because there have been tsunamis, for instance, in Puerto Rico and the Virgin Islands and places like that. And there's a consideration, could we have a tsunami along the Atlantic coast, even here in New England?
The
And
next
my
question,
opinion-
that's your idea, that's your...
My opinion is, yes, we could.
Could you go into that? Because I thought we never had anything, you know, on the Northeast Atlantic. But your work has indicated, criminy, we get these little earthquakes all the time, but they, I think, did you call them a cluster? That's what you look for?
Swarm.
Anyway, a swarm.
Yeah, a swarm.
Okay, close.
Okay. Yeah, so let me tell you about the
Yes.
story of 1929. 1929, there was an earthquake of magnitude 7.3 that was centered just south of Newfoundland on the Grand Banks. You kind of have the land in one area, and then the land slopes off and it's covered with water, and you have the continental shelf. So the water's not very deep. It might be 50, 100 feet deep, but it's not deep ocean. And then the ocean floor drops off to the deep ocean, and that's where you get then what we call the oceanic crust that was created by the hot upwelling at what's now the Mid-Atlantic Ridge. Okay, so in 1929, there was a 7.3 earthquake that was centered right at the edge of the continental shelf, right as you go to the slope. And it caused strong shaking in Newfoundland and Nova Scotia. It was felt in Boston. It was felt in New York City. Not very strongly, but people felt it. Well, that night, a tsunami that with water waves higher than 10 feet came on shore in southern Newfoundland and actually devastated some villages. They had people literally killed in this tsunami. Now, 1929, we already had telephone between North America and Europe, and there were a number of telephone cables that went along the ocean floor. Well, the earthquake apparently triggered a submarine slump. So sediments that were on the bottom of the ocean on this slope that goes down to the deep ocean actually slumped down and broke these telephone cables.
Oh my goodness.
And that probably contributed to helping cause the tsunami. But they had 10 to 20 foot waves come on shore in southern Newfoundland with smaller waves detected, for instance, along the Nova Scotia coast. Okay, so that's up in Newfoundland.
Right.
So you say, can that happen here, for instance, along the New England coast, Massachusetts, Rhode Island, Connecticut,
cities,
New Hampshire, Maine? Well, in 2012, we detected an earthquake offshore east of Boston, right again at the edge of where the continental shelf and the continental slope come together. And then we detected another. And then we detected
my
another.
goodness.
And in the end, we had over a dozen earthquakes from that particular locality, all occurring within a couple-day time period. Ironically, 2 days later, there was an earthquake up at the Grand Banks of Newfoundland also. Same kind of setting.
Yeah.
So I and a student have studied that particular earthquake swarm, and except for the fact that the earthquakes are much smaller, it looks very similar to what happened up at the Grand Banks.
I see.
So what I tell people is any place we have smaller earthquakes, we have the potential for a larger earthquake. So in my opinion, we could have a strong earthquake in this area along the continental shelf of New England, and if we did, there would be a possibility of a tsunami coming on
That's
shore
very interesting.
in the Gulf of Maine and affecting the New England coast.
The shelf is not that far offshore, is it?
No, you're talking about, maybe 100 miles to where these earthquakes occurred.
Right,
So,
and it's a sharp drop, isn't it? Or is
relatively
it?
sharp. I mean, you could walk it, but you know, it would be comparable to a very good slope.
In any case, there would be that possibility that you could have a very strong earthquake, in fact, and that you could even have a tsunami. You mentioned that in this Newfoundland case, the tsunami came actually quite a lot later than the earthquake, right?
Well, but that's because it takes the water time to flow on shore.
I see, yeah.
So when we're talking about quite a bit later, we're talking about an hour, a few hours later.
Okay, yeah. Okay.
You know, even in the case of Japan, you had the big earthquake.
Yeah.
It took the water 15 or 20 minutes to go from where the earthquake was on shore.
I
So
see.
people had felt the shaking, and it had died away before the tsunami came and inundated.
You mean this
in
Fukushima one?
Fukushima.
Okay.
Yes.
Okay. Well, that's nice then. Cheer us right up. And so today you have spectacular equipment, I think. And could you tell us what you do, how you evaluate these signals, and the Weston Observatory and so on? Can you give us some background?
Absolutely. So today, even though we still run at Weston Observatory, the drum recorders that go around, and you can see the pen and watch the line write. In fact, the way we really want to record is on a computer, because then we can do sophisticated computer analysis of the seismograms.
I see.
And then the other thing that's wonderful is the internet, because it allows us to transmit seismic data from any place to any place else. So Weston Observatory receives seismic data from seismic stations scattered throughout New England. We now cooperate with our colleagues in Canada. They send us seismic data from their seismic stations in Canada. We can see seismic data from other parts of the world. For instance, if I wanted to, I could get a seismogram from Bermuda of our local earthquakes. So all of those data now are being sent by the internet to Weston Observatory. It's being received constantly, 24 hours a day, 7 days a week. And we have several computers that are receiving the data. And then we have computer programs that are constantly analyzing the data and looking to see, you know, what it recorded. Is there something that could be an earthquake? And now we have computer programs that if it thinks that there's an earthquake signal on one seismic station, it checks the other seismic stations. And if it gets signal on several seismic stations, it says, oh, this looks like an earthquake. Then it says, okay, well, let's put all of those data together, and now let's try to get an automated location and an estimate automatically of the magnitude. And so within 5 minutes of an earthquake happening in our region, then the computer says, oh, I have a location, I have a magnitude, it's passed all of our tests for being real. We're going to send out a text page. So I get a text page, I get an email, my colleagues at Weston Observatory get this information. So within, say, 5 or 7 minutes after the earthquake, I have an idea that an earthquake has occurred, I have an idea about where it's located, I have an idea about how big it is. So just before we started filming this segment, my phone went beep, 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 and I looked at it, and it thought that it was a magnitude 2.0 earthquake up near Montreal in Canada. So after we're done here, I'm going to go check the computer.
You're going to go check that, right?
That's
exactly.
right.
How long have you had that kind of capability where it seems instantaneous? There are two things of having really good data very quickly, and secondly, that you can communicate all over the place very quickly. Is this fairly new?
It's, I would say, 15 years old.
Yeah.
You know, as the internet, the internet started in the 1990s, and as it grew up during the turn of the 21st century, the internet became faster, and we started pumping more data onto the internet. We started writing computer programs that did these automated locations and automated magnitudes, and they became more sophisticated with time. But it's really been since about the year 2000 that this capability has been pretty widespread, and it gets better all the time. So not only do I get emails from my system, but the Canadians send me emails, the U.S. Geological Survey send me emails, and so I within 10 minutes, oh yeah, there's an earthquake, it's over there, okay.
Right, but I imagine that it's very useful that you are able to see global patterns in this respect, or partial patterns. You're not just local.
We're not just, that's exactly right. That's exactly
which
right.
is terrific.
So if there's an earthquake, for instance, in Alaska, if the waves are strong enough here, I will get text pages from the U.S. Geological Survey with the magnitude and the location, and I will get locations from my local seismic stations, because when they get the waves, they'll also do a location, and they will send it to me.
It's amazing. Let me ask you, if remember in that horrible thing in the Indian Ocean, there are monitoring devices in the oceans. Are there not for earthquake activity? Is that a mistake?
There are a few. There are not
there aren't a lot.
many,
I thought they had them.
There are a few. There are not very many, and that's because they're expensive. And so what they do is places where they know that tsunamis are frequent and can be triggered. They have buoys that have basically pressure sensors and the height of the water. If the water gets high, it says, oh, a little excess pressure, and it sends that to a satellite. But those are put in a few strategic places so that after the earthquake, they will know when the tsunami is, and they'll have some idea about how big it is, and they use that for the tsunami warning systems.
Okay. But I thought maybe they were abundant at this point. That
I would love to. I would love it if they were abundant, but the governments don't spend that much money on this work.
I see. Now, you have done work for monitoring nuclear activity as well. Tell us about that. What's the difference between that kind of seismic activity and earthquakes? Can you distinguish it easily?
We can distinguish it, but I wouldn't necessarily say easily. When nuclear testing went underground in 1962, it was realized that the primary way we were going to be able to monitor the Nuclear Test Ban Treaty was by using sensors that would detect seismic waves. Because an underground nuclear explosion would send out seismic waves just the way an earthquake would.
I see.
And we had some idea about what differences there should be, but we needed to document that. So starting in the 1960s, there was a very large field of nuclear test ban treaty research.
I see.
And studying earthquake signals, studying explosion signals from nuclear tests, studying explosion signals from non-nuclear tests. Because, just because you see an explosion doesn't mean that it's a nuclear explosion.
Right.
So we've been working, and when I say we, I'm talking about the entire seismological community has been working for many years to distinguish these. We now have a good idea about when we have an explosion as opposed to when we have an earthquake. My system at Weston Observatory is one that if it thinks it's got a quarry blast or some sort of man-made explosion, it doesn't send me a text page because it says, I think this is an explosion, not an earthquake. Sometimes it's wrong, but most of the time it's right. Now, then the next question is when there's an explosion, is it a chemical explosion or is it a nuclear explosion? And that's cutting to finer details, and that's a harder problem. And it's not completely solved, even though the politicians want to be able to say with 100% certainty, this is a nuclear explosion, this is a non-nuclear explosion. And I would say we're probably 95 or 97% there.
I would have thought a nuclear would be substantially greater than, say, something from mines or an underground explosion of some sort. I guess volcanoes, though, would be large,
Well, but sometimes construction, mining companies set off very large chemical explosions. You know, if they're trying to break up a great deal of rock, one big explosion might be a lot cheaper than it is to drill a bunch of little explosions and pull the rock out. So you have that, and then what countries have become more sophisticated at over time is reducing the sizes of their nuclear explosions. Because they're not trying to test the whole bomb. They're actually just trying to test little pieces of the bomb. They want to know, will the trigger work properly? Will they start the ignition of the nuclear reaction? Because once they start, they know they can keep it going. So they're oftentimes just checking the triggers. They're testing to see, does this start the process the way we want? And that's not a large explosion. So you can have a lot of overlap between the sizes of these things.
I see. I didn't realize that. I thought, no, they had to drop the well or put them deep in the ground or something. Well, that is quite interesting. But now you've got this pretty refined, I guess. And I guess they still monitor certainly plenty of nuclear warheads around that.
And testing, for instance, North Korea. North Korea has done some testing in the last several years, and they've claimed they've done some testing. And there's been a great deal of research that's done on that. And of course, some of the research is classified, so I don't have privy to it, and even if I did, I couldn't tell you about it.
In terms of your work, you do a number of these things. You're a busy man. But in terms of this work, was there a reason to settle on the East Coast, or the East Atlantic in particular? Was there a particular interest there?
The interest was I got offered a job.
There you are. Same old story. We hear this all the time, right? Okay. But I was just curious because that's, well, I guess we're not aware of having so much activity. But now that you've wakened us up, we can all be more alert. But it is
well, what happened was, I finished my Ph.D. in California. I had studied earthquakes in California. And which was a tremendous place to, I tell people, cut my seismological teeth.
I bet.
And then the job became available at Boston College and at Weston Observatory. And I started looking into it, and I realized there were earthquakes. In fact, if you went back to read literature from the early 1960s, We knew about the 1755 Cape Ann earthquake. We knew about a big earthquake in Southern California in 1857. We knew about a big earthquake in Northern California in 1906. All three were considered damaging. So in the 1960s, people thought that Boston and California had the same seismic hazard, that, you know, the same potential for damaging earthquakes, because both had damaging earthquakes in their histories. Well, we now appreciate that California is more dangerous than Boston, and the reason is because the earthquakes are much more frequent in California than in Boston. But we do have a history of damaging earthquakes. So for me, it was interesting to come to a place where there was relatively little known about the earthquake activity and relatively little research that had been done, after California, where you have, you know, dozens of schools that are doing research, you know, dozens and dozens of seismologists.
So this was wide open for you.
So this was kind of wide open, and what was exciting for me was to come to this part of the country and to realize how much of what I studied in California applied directly here also.
Isn't that interesting? And that, because we do have all the earthquakes happen on the West Coast, we're perfectly safe here. But what you're saying is no.
No, we're not perfectly safe. We're safer than California, but we're not perfectly safe.
Right, but it's a matter of activity, the relative activity. It's not like the East Coast or the Atlantic is a little more peaceful, or potentially it could be quite active.
Well, what I tell people is, in California, if you run seismic stations and monitor for 1 year, and then you come to New England, let's say, same area, same size area, and you put out seismic stations and do the same kind of monitoring, you have to wait about 100 years to maybe 150 years to get the same number of earthquakes as you get in 1 year in California. Both places, it turns out, the distribution of the earthquakes with magnitude is the same. So for every one damaging earthquake, let's say magnitude 6 you get in California, you get 10 magnitude 5 earthquakes, you get about 100 magnitude 4 earthquakes, you get about 1,000 magnitude 3 earthquakes, you get about 10,000 magnitude 2 earthquakes. Same thing is true in New England. For every one damaging earthquake, about 10 magnitude 5s, 100 magnitude 4s, 1,000 magnitude 3s, etc. But now it's those play out 100 times slower than in California.
But the Earth is moving, right?
But the Earth is still moving. The plates are still moving. So you know, where they have a damaging earthquake once every 2 or 3 or 5 years in California, we have a damaging earthquake once every 200 to 300 years, maybe 500 years in New England.
Right. Let's keep it that way. Yes.
Well, our last really damaging earthquake was above magnitude 6 was in 1755. So that's over 250 years ago.
Right. Does that make you worried that maybe something could happen soon, or?
Well, people will come to me and they'll say, Dr. Ebel, they say we're due for an earthquake. And the first thing I say is, I'm the they. But the second thing I say is, I can tell you what the averages are.
Yeah.
But the problem is, averages are not predictive.
Yeah, I see.
And so I don't know if we're due or not. So if you have an earthquake, and you have another, say, strong earthquake a year later, and you have another strong earthquake 99 years after that, the average time between those earthquakes was 50 years. But the 50 years is not predictive, because you had a short time period, you had a long time period between the earthquakes.
Right. The Earth doesn't go by these regular calendars.
It doesn't have a regular calendar.
Right. Okay. So in our last few minutes, I would like to ask you about your work. Is there anything in particular that you really enjoy the most? What's the most exciting thing?
I think the most exciting thing is that as we study earthquakes more and more, we're starting to see the patterns, where they occur, which, for instance, in this region, which might be the faults that are active. California, which might be the faults that are active.
I see.
We can't predict earthquakes, but we're getting a little bit better at assessing when there are times when the Earth has a higher probability of having earthquakes.
I see.
And particularly strong earthquakes. But the patterns are subtle. And that makes them interesting from a scientific perspective, but challenging also.
Right.
Because I would love to be able to give you the answer today on when the next damaging earthquake will be, but I can't do it.
Right.
If the patterns were obvious, people like Charles Richter would have figured
Yes,
them
that's
out
right.
100
A
years
long
ago.
time
Richter was a very smart man.
Yeah,
He was a good
yeah,
seismologist.
yeah.
I met him. He
Oh,
was-
did you?
Yes,
Wow.
in his late years. But he couldn't see the patterns either because
Right.
the patterns are very subtle. And that's
Right.
why we're still so surprised by earthquakes. But every time an earthquake occurs, I learn something new.
Yeah. Yeah.
And that's a very exciting thing. You know, a research scientist in a laboratory, they only learn something new when they go run their experiment in the laboratory.
Yeah.
I can be sitting here, and if an earthquake occurs, I'll look at the location, I'll look at the magnitude, I'll go and collect more sophisticated data, and I will say, oh, gee, I didn't expect that. Or,
Yeah.
oh, gee, that's exactly the pattern I've seen before. And look, this is repeated several times.
Right.
So I'm always learning something new.
I think that's the scientific mentality. You're always happy to get a surprise, get the new information, have to figure something out. Right?
Well,
Yeah.
and it's like a huge puzzle, and sometimes you do fit a piece into the puzzle.
Yeah, right. But what an exciting time to be doing this, it seems to me, because so much is global in terms of information, and it might be easier to put patterns together, I'm not sure.
It's definitely easier. Computers
yeah.
are helping us
Yeah.
with that. We have new mathematical
Well, I was
methods
gonna say, you do
that help
modeling,
us look
yeah.
for patterns.
Yeah.
You know, with computer clusters and supercomputers and things like that, we can do processing that we couldn't even have thought of even 15 or 20
Yeah.
years ago.
Yeah.
So it's really exciting because there is so much we're learning now about the Earth.
Yeah. Is there anything that's particularly frustrating in this line of work?
I think the most frustrating thing is the fact that government funding for research in general is going down. So
Yes.
here, you know, more money would allow us to make faster advances, and the government says, well, actually, there's less money available this year than there was last year. And so, you know, when you have fewer people working and you have less equipment to do the work, the discoveries just don't come as fast.
I don't know if the audience is aware, this is very widespread across fields, that there's this cutback and cutback, and if we could have for science what we spend in 1 week in Afghanistan, it would really be very welcome, I think, you know, because we could really use the money in many sciences, but there's a situation where you have to train people for a long time and get equipment.
And doing science has become more expensive.
Yes,
you know, 100
sure.
years ago, people would buy a seismograph, and they would set it up, and then they would run it. And they would look at it and say, okay, it's running, and there wasn't that much to do. Now you have computers, they need to be programmed, they go obsolete, so you have to put new computers in. The equipment constantly needs to be calibrated. The equipment, because it's very sensitive, can very easily go amiss, and so then it needs to be fixed or it needs to be replaced. And so there is a much larger cost with doing seismology than there was, let's say, 100 years ago.
That's an interesting point. Yes, everything becomes obsolete quickly, I
Well, it
suppose.
becomes obsolete, and some people don't like that. But on the other hand, I love it. And the reason is because when I have an obsolete computer and I do get the funds to buy a new computer, my computer is not, I don't buy the same thing. I buy something that's maybe 10 or 100 or 1,000 times better.
Yeah, that's a nice thing. Before we close, can I ask about the Weston Observatory? Can the public visit places like that? Are they just their laboratories or whatever?
We are set up so that the public can tour the observatory. The only thing is, we used to have a regular tour guide and Boston College.
But the funds have been cut.
But the funds were cut, and so Boston College took the tour guide away.
Yeah.
So there are restricted times when we can give tours, and oftentimes you don't get a seismologist. But it is possible under restrictions to tour the observatory, so you have to contact the observatory.
Right. It's good to know, because a group could go or a class could go possibly or something like that.
It is possible to do, and
Right.
you just have to contact the observatory and see if there's a time
Okay,
when
I'll
there is
make
someone
sure
who
that information is on the event page. And Dr. Ebel, thank you ever so much for visiting with us and giving us this wonderful information. I wish you the greatest luck and a lot of money in funding exciting.
Well, I appreciate the opportunity because anytime I have a chance to educate the public about earthquakes, I think it's important to do.
And they love to hear it. Thank you very much.
You're welcome.